All right, guys, what questions do you have about the homework? Are we good? Okay. Well, and that's actually one of the, so this, remember how I told you that this assignment really took some effort to pull together? Yeah, I'm sure, well, I'm not sure. I was hoping it wouldn't be the case. But guys, yeah, please show me the errors in my ways as well. So Ami, you got in there first. What do you see? Okay, so let's go to 11 and make sure that the confusion isn't my answers. I think these are right. So guys, looking at number 11, the question is, are these processes spontaneous? And guys, just by way of teeing up this ball, if you remember, we talked about the idea that the big idea for this entire unit is spontaneity. And guys, today's the last day of the unit. So, remember, as we talk about spontaneity, it's not only the big idea, it's the stuff that we introduced over the last couple days. So guys, spontaneity is a reaction that happens on its own without outside intervention. Looking at number 11, number 1, does a banana ripen on its own? You bet. Does sugar dissolve in coffee all on its own? Not that you would know, but you've probably seen pictures of coffee and, tongue now removed from cheek. The reaction of nitrogen to form diatomic nitrogen with atom gets to the thing you want to dig into deeply. But the idea here, guys, is nitrogen exists as diatomic nitrogen all on its own. That's spontaneous as well. We good there? Then letter D, lightning?
That's spontaneous.
Yeah, depending on which superhero universe you adhere to, still spontaneous.
I would love for lightning to be done spontaneous. I would love to be able to just
Equal and lightning.
Just like throws it out, like there's like some person in a government building somewhere just like throws switches to figure out. He like pushes the button after like.
All right, guys, letter E. Hold on. Formation of CH4 and O2 from carbon dioxide and water. That is not spontaneous. But guys, this brings up an interesting thought. So what this is saying is methane and carbon and oxygen forming from carbon dioxide and water. That is not spontaneous. What is spontaneous? The other thing. Right? That's what Bunsen burners do. So then you're thinking, wait a minute, but remember, spontaneity does not get yes or no'd based upon whether there's that initial activation energy like the sparker that gets your burner burning. So, what were you having problems with in that? Did I get them right? Oh, look at me. Okay. Yeah? So, now my tongue's out of my cheek. So coffee's hot, but it's also in water, and sugar dissolves in water. Right? So where was the problem in B?
Just that it was
Yeah. What is it? Is it the sugar? Sure, but yeah, so the sugar can't jump into the coffee cup, but once it's in there, it does it on its own. Is that okay? Yeah. Other questions, y'all? And please lead me to potential errors in the thing as well. Nathaniel. Oh, you know what? Let's look. I think it may have been one where the question changed and I meant to pull number 4 out of the... Let's look. Yeah, here, let's do this. Digging into here. So, questions. And so this was number 4, and this seems to have done it in its entirety. Then if we go to number 4 here. Right. So it says predict the signs for delta H and delta S. Oh, so that's the thing that changed, is this question in the old book only had delta S. So guys, can we talk about this? So Nathaniel, you are proposing that delta H is positive. I'd buy that. I think. So I would have never came up with that, because I guess I would have looked at that crystal and not thought about the bonds inside. But I like, guys, any other thoughts on that for delta H? Did anybody argue negative? Go ahead. Oh. Wait a second. Hold on. Is number 4 the one down below? Oh, hold on. So 3 is referring to the solid on the left. Oh, no. I was 2. No, I was 2. Okay, so 4 is down. Okay, now we're on the same page. So 4 is looking down. Okay, so now let's talk. Now I agree with you totally. Yeah. So now I'm grooving, because you're right. Bonds are being broken and there's greater disorder. So I was looking up like you were. So both reactants or products are gases. However, there are twice as many moles of product. As such, delta S will be positive. In addition, oh wow, delta H will be positive because, good night, because bonds are being broken. Woof. Okay. So, and then is number 3 okay? Okay. Good. All right. So guys, other thoughts that might be my issues or just places you need support? Is everything else okay?
27.
Okay, let's look. So 27 says, and hold on, are we doing, so 27 just A and C?
Yeah.
Okay, and here I'm going to bring this down, I think. Okay, so 27A, what sign for delta S do you expect when the volume of 0.2 moles of an ideal gas is increased? So volume goes up, there are more places that the particles can be, they're more spread out. That would be a positive delta S. Is that okay?
Yes.
Okay, so C, which of the following statements about this process are true? Which process?
Process of the ideal gas being considered. But the thing is, like, the answer for C just doesn't.
Oh, it's got parts. So this should have 3 answers, right? And that is not one of them. All right, so this is now a bitty eye, and it says this. Which of the following, okay, the entropy change you calculated will be the same for any other, what?
B is about calculating entropy change, which we haven't done yet.
We're never going to. Oh yeah, we are. No, we are. No, we're not going to do entropy change in that form. We'll do entropy change for reactions, but not phase changes. Okay, so what is this saying? Which of the, okay, so the entropy change you calculated will be the same for any other constant temperature. But, right. But is that something you guys understand? Because we're not, there's an equation in here where you can figure out entropy based upon temperature. Do you guys, like, should I leave CI? Like, does that make sense to you? That entropy is temperature dependent, and therefore if you change the temperature, you change the entropy? Is that okay?
That's why I was confused, because in the answer sheet in the back,
Oh, no, it is true. Because the products, or whatever you want to call it, it's a change, right? It's going from one state to the other. And if the temperature is higher, if the temperature is higher, the change in entropy will be the same, because the beginning and the end will both have proportionally higher entropies.
It's like the entropy change.
Yeah, you would have never come up with that, right?
Okay.
Okay, so let's get rid of I. So then what about double I? The value of delta S you calculated. You know, guys, we're just going to get rid of C. Because, no, seriously, because you haven't done the calculation in B, so you have really nothing to base this on. So we're just going to do 27A in the future. Where did it go? All right. I think that's a fair solution. Are we good other than that? Good? Okay, so guys, let's save this. Let's jump out of this. Let me add this. So we're going to call this entropy. We're going to score this. So Ami, oh shoot. Ami, were you good?
Yeah.
Where's my mouse? There we go. And Anna. Oh boy, oh boy. You guys, here we go. So guys, looking, let me get you on the right page here. But guys, I'm going to need you to sort of do something here. I want you to be ready to jump into this, but I don't want you to camp here yet, simply because we need to lead into this idea. And if you, my experience has been, well, here, let's just do it. Page 822. Go to page 822. Okay, so guys, looking at the bottom of page 822, you'll notice there's a table down there. And guys, this table is the big idea for chapter 19. It talks about spontaneity. So guys, let's talk for just a second. Look away from the book for a minute and let's review. So guys, in chapter 5, we talked about enthalpy, right? Heat, in and out. And so guys, what reactions tend to be spontaneous relative to enthalpy? Enthalpy going out or enthalpy coming in? Enthalpy going out. Those are exothermic, right? Processes that tend to be spontaneous are exothermic. Then guys, we talked in chapter 19 about entropy. What entropy changes tend to be spontaneous? Entropy up or entropy down? Entropy up. So now, guys, we've got these two factors, enthalpy change and entropy change, and they both relate to spontaneity. So, guys, that, looking on page, let's actually go back a bit. Looking on page, where does it introduce it? Oh, on page 817. Guys, this is the tiebreaker. Looking at the bottom of 817, guys, this is how you know a reaction is spontaneous. And guys, this is an always never situation, which we never have in this class. But guys, this is an always. You can determine whether or not a reaction is spontaneous based upon its change in Gibbs free energy. And that is an ironclad answer to the question, is it spontaneous? Guys, understand in this class there's only one other way to tell if a reaction is spontaneous. Voltage. And we're going to do that in chapter 20 at the very end of the year. So guys, this is it. That little harmless equation at the bottom of 817 is the answer to is a reaction spontaneous. But now guys, this. Look at, well, not obviously, G is Gibbs free energy. Thank the Lord we actually have an abbreviation that makes sense. But guys, what is H? Enthalpy. What is S? So guys, that's what this does. Gibbs free energy brings together enthalpy and entropy. But guys, now turn back to page 822. Guys, looking at page 822, right under 9.19.6, you'll notice this is the same equation rewritten with deltas in it, because what we're going to talk about are changes. So we've got change in Gibbs free energy, change in enthalpy, change in entropy. But guys, what else do we have in this equation? T, which is temperature. And guys, that leads us to the equation down at the bottom, or I'm sorry, the table down at the bottom, because what you're going to be asked to do is predict under what conditions is a reaction spontaneous. And guys, that's where we've got to get. But what I find is if we just jump hot into the middle of that, no pun intended, it's going to be a problem. So guys, what I'm going to ask you to do, and if you don't think you can stand the temptation, put something in your book on that page and close it. Guys, we're going to build up. It's going to take us 10 minutes, but we're going to build up to that table. And then guys, we're going to spend some time and really tear that table apart. As a matter of fact, you know what I might do? Say no, because you don't know what I might do. No. What might you do? I'm going to print it for you. Big. Bigger.
Oh.
Now it's sideways.
Bigger.
All right. Okay, guys, I did not print your notes for you today, but hopefully you're beginning to get comfortable with the idea that not everything that goes on the screen needs to go on your paper. So guys, for example, this is what we just talked about. So guys, this is where we are right now. Chapter 5 told us that reactions that tend to be spontaneous are exothermic. They have negative delta H values because heat is going out of the process. Then guys, we said from chapter 19 that spontaneous processes tend to increase the entropy of the system. We know the universe always goes up, but guys, this tends to increase the entropy of the system. So guys, that's where we are right now. You guys okay with those ideas? Questions or thoughts there? Okay. So guys, as we just mentioned then, this is where the idea of Gibbs free energy comes in. So guys, in order to finally predict the spontaneity of a reaction, what we need to do is we need to bring these together, and that's Gibbs free energy. So guys, some of this might be worth writing down. So when we talk about Gibbs free energy, I don't know, your call on this. It's a thermodynamic function that brings together enthalpy and entropy. Then guys, I don't know if you need this. It's abbreviated G. We know that we've got this equation from the bottom of the previous page, but guys, this is how we work with this. We talk about changes in Gibbs free energy because it's these changes that allow us to predict spontaneity. But then guys, you're going to find we talk about this in sort of a weird way. So I want to show you. You guys okay? I want to give you time. We have a lot of time. You guys okay? So guys, this then is where we are. We said that this is one of the two ironclad ways to know if a reaction is spontaneous, which is the big idea for what we're doing. And it goes like this. Guys, if delta G is negative, the reaction is spontaneous. But notice we add this little caveat in the forward direction. And guys, what if delta G is 0? What if delta G is not changing? And that would make it not but it would make it equilibrium. Yeah. So James, normally people say equilibrium, but don't get the reversible idea. So guys, if our delta G is 0, this reaction is at equilibrium. But guys, remember that means that it is reversible. Right? So reversible means goes forward and backward without changing the system or the surroundings through the same pathway. So James is right. It's reversible, and therefore it's at equilibrium. Hey, I'm sorry. Oh yeah, no, she's gone today. Yeah, thank you though. And then guys, what if delta G is positive? Is it spontaneous? Actually, weirdly, the answer is yes, just in the other direction.
So you have to force it to react and then
Yes. Or you just flip it around and then it goes that way on its own. So guys, the idea is this. If delta G is positive, the reaction is not spontaneous in the forward direction, but it is spontaneous in the reverse direction. Ugh. And guys, I know that this feels kind of like word games, but that's the way we talk about this. So if we're studying a process and delta G is negative, spontaneous. If it's 0, it's equilibrium. If it's negative, it's not spontaneous that way, but technically it would be spontaneous in the other direction. Because amazingly, we're almost done. Yeah. Yes.
So for the only way that something would have some kind of spontaneity is equilibrium.
Yeah, but then that gets, and again, it's word games, right? So yes, if something is at equilibrium, see, this is where it gets weird, because technically it's spontaneous in both directions. I know, right? So, but understand, we don't call it spontaneous, we call it equilibrium, because the net change is 0. It's doing and undoing itself spontaneously in both directions, so there's no net change. So then your other choices are spontaneous this way or spontaneous that way. So really, technically, if something's at equilibrium, nothing's changing, but something is happening. Isn't that weird?
So is there nothing that can't be spontaneous?
I mean, you can force that by separating things. If the methane and the oxygen never come into contact, nothing happens. But if you bring them together and provide the opportunity for something to happen, it's either going to happen one way or the other way or equilibrium. Yeah, crazy, right? You guys okay on this? Okay, so guys, with that said then, grab your AP equation sheets. Who needs them? You guys okay? All right. I got you. Is that from general chemistry?
Yep. I keep everything in this one.
You're a genius. All right. So guys, how then do we think about Gibbs free energy? And again, it's hard for us to picture entropy, disorder. It's getting better, but it's hard. So guys, in the same way that we understand that balls roll downhill because they release energy, if you can just take that mental model and replace it with Gibbs free energy, then all of a sudden, guys, the model gets even better. So here's what we then know. Any spontaneous process, Gibbs free energy always goes down. And that is a hard always. Guys, in any spontaneous process, Gibbs free energy always goes down. So then the question is, how do we calculate it? Oh my gosh, this looks familiar. Right? Oh yeah. And again, guys, as we've said, if delta G is smaller than 0, if delta G is negative, it's spontaneous in the forward direction, it makes products. If delta G is bigger than 0, it's spontaneous in the reverse direction, and it favors reactants. Did that make sense? Is that an okay connection? Let's let you simmer on that for a minute. Let everybody finish scribbling and then we'll talk about it. Again, I'm constantly afraid I'm in your way. Okay, if I ever get in your way, just like shoot something at me. I'll move. Oh yeah? Oh my gosh, who was that last year? It was the kid that sat where McKenna's sitting right now. And, never mind. So in the next unit, we're going to start talking about how photons of light transfer energy. And they're surprisingly like Nerf darts. And I may or may not have a Nerf gun. And I almost made him cry. But finally he got smart and he used his binder as a shield. Yeah.
You're just like shooting him forward.
Oh yeah, but they were whistle darts, so that made it worse. Yeah.
But like,
Yeah.
like, just like you were just like unloading on him or just randomly going to
Oh no. It was well no, because light, streams of photons, right? It was all it.
You were
Yeah.
just like going.
I think this time, never mind. All right, we're gonna make this even better. All right, guys. So
Well, this time we used it on Spencer.
Nathaniel, you had a thought.
What does favors mean in this context?
Yeah.
It's not spontaneous. If it's only spontaneous in one direction,
Yeah.
it can't be like we're talking about equilibrium.
Yeah, so here let's so guys, you're beginning to get this sense, right? That in this class, one of the things you need to do to be successful is you need to become a master of ambiguity, right? You never get to say always or never, because the minute you do, you're wrong. So let me put this in a different context for you, Nathaniel. So we talked about Le Chatelier's principle, right? And so we talked about the idea, hold on. This could take a minute, but let me get us there. So we talked about the idea that if we increase the concentration of A, same side does the opposite side does the same. This would go down and these would go up. Is that okay? So the way that we talk about that is we say that the equilibrium shifts to the right. Is that okay? But then we also talked about Kc values. And the Kc value, did that wrong. The Kc value is products divided by reactants. So it'd be the concentration of C, the concentration of D, the concentration of A, and the concentration of B. Is that okay? And so guys, track with this idea. So Le Chatelier's principle tells us that if we increase A, it shifts the equilibrium to the right. But now how do we talk about this? So guys, imagine we get the Kc value, and the Kc value is like 1,000,000. What does that tell us? If we have a Kc value of 1,000,000, which is bigger, the top or the bottom of the fraction? The top. But guys, the top are products. So now listen carefully. If we have a Kc value that is bigger than 1, that tells us that there's more products than there are reactants. Is that okay? So how do we talk about that? And the way that we talk about it is with the word favors. We say that Kc values bigger than 1 favor products. So when we say favor, we mean that there's more of the one than the other. together. Is that okay, y'all? Do you see how favors works? But now, guys, apply it to this. So let's apply it to this idea right here. So, guys, delta G less than 0. That means delta G is negative, right? So imagine that we have some reaction, and this reaction has a delta G that is negative. Is it spontaneous as written? Yes. That means that it favors products. So if delta G is negative, less than 0, guys, if delta G is negative, it means the reaction is spontaneous, it's going on its own, and it makes products, so it favors products. Now, guys, what if delta G is positive? Is it spontaneous in that direction? No, but it's spontaneous in the other direction, and that means that it's making reactants, so that favors reactants. Is that okay? You're good? Okay, so now, guys, do this. Let's gather around our AP equation sheets, and let's camp there for a second and make sure we're clear on this. So, guys, looking on the page 4 side, so let's go through the thermochemistry stuff. But, guys, notice thermochem and electrochem are together. That won't make sense until chapter 20, but here we go. Do you need a copy? So, guys, first equation under thermochem. Got that nailed down? Q is equal to MC delta T. You good? Okay. Guys, remember you don't have to memorize the value for C, but we got that equation down. Now, guys, let's go through the next 3 equations because, guys, they're a little bit different. So first of all, what's missing from those 3 equations? N, the number of moles. So, guys, I guess in theory you could write in the N's, but understand when you see this on the AP test in May, they're not going to be there. So hopefully you can remember that there are N's in all of these. But then, guys, look at the second and third equations. Delta H and delta G. Guys, notice that the delta H and delta G equations are all products minus they're all products minus reactants. But, guys, notice in the delta H and delta G equations, these are heats of formation and Gibbs free energies of formation. But then, guys, notice up above, for the entropy value, these are not entropy changes of formation, these are entropies. So, guys, substances are screwed up all on their own. It doesn't matter how they got there. They have screwed up values, entropy, but, guys, notice that the enthalpy and Gibbs free energy numbers are of formation. So the enthalpy change of formation, the Gibbs free energy change of formation. You guys good on those? Another thing to think about as you're moving towards the test, entropy changes tend to be in joules. Delta H and delta G tend to be in kilojoules. Just so you know. Then, guys, finally down below, you'll notice we've now got our delta G equation. This says delta G is equal to delta H minus T delta S. But then, guys, down below that, you'll notice you've got 2 more forms of the delta G equation. Guys, you do not need those now. The second one is for gases, and the third one is for batteries. Okay, so the E in that third one is actually voltage. So the second and third of these we'll talk about during the gas unit, and then chapter 20, the last unit, the batteries unit. And then, guys, the one down below that is also a battery equation. The L current is equal to Q divided by T, and we'll talk more about that later as well. So, guys, are you comfortable then with how all of these equations work? You're good? Okay, because you need to be able to do this math. But, guys, it's amazingly repetitive, right? The second, third, and fourth equations are all the same. It's just one's for delta S, one's for delta H, and one's for delta G, but the structures are fundamentally the same. You guys good? Then as you're doing this math, please remember, guys, you need to write down the equation. Then you need to rewrite it for the specific reaction you're studying. Then you need to plug in your values. Then you need to solve it. Any questions about any of that? You guys ready to wrap up the unit? Okay. Guys, open up your books then to page 820. Oh, wait, I'll give you a copy. Never mind. You don't even need your books. All right. Let's wrap this up. Oh, I may have run out of paper. We'll see. Dallin, you know that Pop-Tarts are actually not food, right? Yeah. It's dessert disguised in Mylar.
Anything that's sugar in the first 3 dessert.
Yeah? Oh, yeah. All right, guys, let's set the stage. Goes like this. So, guys, here's what we now know. We know that we have this equation. And guys, in order for this conversation to make sense, guys, we need to understand how this equation needs to be chunked. And then I'm going to share with you the way that I think about this. So guys, let me do that first. Ready? We're going to have a strange conversation. This conversation has one intended outcome. Is a reaction spontaneous? That's it. Guys, understand this equation allows us to calculate delta G, but it also allows us to make predictions. So guys, that's the big idea for this unit. We are going to use this predictively to say, is an equation spontaneous? Now guys, here's what we're going to say. You ready? Spontaneity is good. Spontaneity is good. That's going to be our frame of reference. Spontaneity is good. Non-spontaneous is bad. Right? Spontaneous good, non-spontaneous bad. Do not use those words on the AP test because they don't know what you're talking about. Yeah, huh? What? Good? Really? But guys, you're going to find out this is a battle between good and evil. You ready? All right, so let's set the stage for the battle. Guys, delta G is free energy. Now, what free energy values are good? Negative. Let's do it again. Guys, what Gibbs, change in Gibbs, what delta G values are good? Negative. Does that make sense? Guys, the logic goes like this. What delta G values are spontaneous? Negative, like a ball rolling downhill. Guys, you got to understand that. For a reaction to be spontaneous, delta G's got to be negative, but we're going to call spontaneous good. Yes? Now this. Guys, this thing has got an enthalpy component to it. Guys, what enthalpy values are good? Talk to the person next to you. What delta G values are good? Turn and talk to Dallin. You know what, James? Do this. Why don't you just move back? Because there's a lot to talk about. Yeah. Yeah, no, I know. She emailed me. Thank you. All right, guys, so let's talk. You've got to understand this frame of reference. So what we're saying is spontaneous is good. So guys, let's not overthink this. What kind of reactions tend to be spontaneous? Exo or endothermic? Exothermic. So guys, what delta H value associates with exothermic? Negative. Now guys, what about, and so we're going to say negative delta H is good. But now guys, this, I'm not going to do the good or bad. Let's get to the underlying idea. Guys, what kinds of reactions tend to be spontaneous? Ones that increase disorder or decrease disorder? Increased disorder. So guys, let's do this. What delta S values are associated with an increase in disorder? Positive or negative? Positive. So now guys, we've got the idea that this is true. So, bump. So guys, this then becomes the idea. What delta G values are good? Negative. What delta H values are good? Negative. What delta S values are good? Positive. So now guys, we've got to do one more thing and we're ready to go. What is T? Temperature. In what units? Kelvin. Guys, what can a Kelvin temperature never be? Negative or 0. But guys, the idea here is this. This value will always be positive. You got that? Okay. Now guys, let's do this. Let's go to our table. So guys, do this with me. Here we go. Let's pick the easy fruit first. And guys, I would encourage you to write this down with me. Let my board turn on. All right. So guys, what Gibbs free energy values are good? Negative. So guys, in all honesty, is it bad that we're using positive and negative? Should we say spontaneous? It's just too big a word. Okay, so I know that you're tired, but guys, at the same time, I'm afraid you're not connecting. So are we okay with the idea that negative delta G values lead to spontaneity, and we're saying that spontaneous is good? Okay, now guys, let's pick the easy fruit. So looking at delta H. Guys, delta H is enthalpy. We know that exothermic tends towards spontaneity, right? So guys, we know that negative enthalpy values, change in enthalpy values, are good. Is that okay? Exothermic. But now guys, what about change in entropy values? What change in entropy values tend towards spontaneity and are therefore good? Positive. But now guys, look at what happens. This negative, and remember this number can never be negative. So when we have a negative delta H and a positive delta S, guys, look at how the math works out. This we think of as a term. So the idea is that we have a negative times a negative times a positive. And guys, when that happens, what does that value always have to be? Ooh. So guys, we've got, wait. No, sorry, this is always positive, my bad. We've got you guys have thrown me off. Guys, we've got a negative here. Temperature's always got to be positive, and if delta S is positive, we've got a negative times a positive, which will always be negative. Now guys, watch. If delta H is negative, and if delta S is positive, this term will be negative, this term will be negative, meaning this will always be negative. Guys, that's what this is saying. If delta H is negative, that's good. If delta S is positive, that's good because it makes this term negative, so delta G will always be positive, so the reaction will always be spontaneous. What did I say? I'm sorry. Guys, seriously, you've totally thrown me for a loop. Whew. So guys, do you get the idea? Delta G will then always be negative, so the reaction will always be spontaneous. Good? Okay. Now guys, let's do this. Cleaning up the mess. Guys, let's look at the other end of the spectrum. Delta H is positive. Good or bad? Bad, not spontaneous. Delta S is negative, good or bad? Bad, not spontaneous. So guys, look at what happens. Again, we've got the negative times the positive times the negative. And guys, when we do that, that's a positive value. So if this is positive, and if this is overall positive, guys, that means that delta G will always be positive. What does that mean? It means it's non-spontaneous at all temperatures. But remember the caveat, the reverse reaction now is always spontaneous. You okay on that? All right, now guys, this is where this gets deep, and we're going to have to do some math. So guys, now we need the tiebreakers, and it goes like this. This is where this gets sort of interesting. So guys, what about this? What if enthalpy, what if delta H is negative? Good or bad? You're freaking me out. Delta H is negative, that's good, it leads to spontaneity. What if delta S is negative? That's bad because entropy change is going down, it's becoming less disordered, and that's bad. So guys, if we want this reaction to be spontaneous, this is in support of spontaneity. This is fighting against spontaneity. So guys, this is bad, and we need to make bad smaller. So how do we make bad smaller? We cool it down. Guys, let that sink in. If delta H is negative, that favors spontaneity. If delta S is negative, that does not favor spontaneity. So we need to make that entropy term smaller. How do we do that? We cool the reaction down. So again, guys, the idea is this. If delta H and delta S are both negative, this does not support spontaneity. So guys, what that means is this reaction will be spontaneous at low temperature, and it will become non-spontaneous at high temperature. Does that make sense? You okay? So guys, let's then look at the other extreme. Guys, what if we then have positives for both of these? So now what we've got is a positive for delta H, that does not favor spontaneity, a positive for delta S, and that does favor spontaneity. So guys, when this is the case, we need to make the effect of the entropy change even larger, so what do we do with temperature? Getting concerned again. Let's say it again. So enthalpy change does not favor spontaneity. Entropy change does favor spontaneity, so we need this to be bigger than this. So guys, to make this bigger, we drive the temperature up. That makes this term bigger, and that can eventually make the reaction spontaneous. So that means that this is non-spontaneous at low temp, and it becomes spontaneous at high temp. So guys, what I'm experiencing from thinking through this with you is there's moments where you're locked in, and then other moments where you're like, you seem more tentative about the ideas. So guys, what I'd like to do is I'd like to give you a second to just chat about this with the person closest to you. Work through, if you have questions, guys, process for a minute, then we'll talk, because this is the big idea. So take a minute. So guys, let's wrap up the thought you're currently in the middle of. So guys, what do we need to talk about? Help me help you. What do we need to talk about, Kenna? Yeah, so, and I don't know if you like these or not, but the examples that they give are actually phase changes. So, for example, liquid water becoming a solid becomes spontaneous at lower temperatures. And then their example is boil or solid to liquid melting, and that becomes spontaneous at higher temperatures. But I don't think that does a good job of satisfying the complete question, which is about the chemistry and not phase changes. So unfortunately, right now, I'm afraid that if I was to give you chemical examples, I'm afraid it would be so abstract it wouldn't be necessarily helpful. I mean, if I were to tell you that the reaction of, the reaction of this salt with this gas at this temperature is not spontaneous, but it is because we heat it, I don't know that that would get us very far. The thing that you will see, though, is that like when we go to do the next calorimetry lab, you're going to be running into spontaneities that have competing temperature and entropy changes. So you will see a little bit of it there. But for now, if you're comfortable with the sort of the abstract nature of this, just understand that if you have either a delta H or a delta S, let's say it differently. If you have a delta S term that favors spontaneity, increasing that by heating it will cause the reaction to be spontaneous. If you have a delta S value that is positive, meaning it doesn't favor spontaneity, cooling that will then tend towards spontaneity. Is that okay? Guys, what else? Adam, good, just a second.
If we cool down our ammonium nitrate friends enough, they go to salt water.
Correct. Yeah. Yeah, interesting, right? I don't know what that temperature would be though, but yeah, I wonder.
Well, if you got it cold enough, then it'd probably freeze the water.
Maybe. That would be interesting. Yeah, so that's interesting because it could be relative to the freezing point of water.
Or if you got it cold enough, water wouldn't have enough energy to pull the ions.
Yeah, right, absolutely. Yeah, James, go ahead.
I was just confused on a conceptual level. What is it when it says the reverse response?
Yeah.
So like you do the reaction and then immediately pushes back.
Yeah, so, hey guys, James brings up a really interesting question. And you noticed this before. So guys, a couple slides ago when we talked about delta G, and we said if delta G is negative, it's always spontaneous in the forward direction, never spontaneous in the reverse direction. And then if delta G is positive, it's never spontaneous in the forward, always spontaneous in the reverse. And that's what this is then saying too. Spontaneous forward, not spontaneous backwards. Let go of it. We say it because we have to, but seriously, you can let go of that idea of reverse. So if you simply understand the idea, guys, let's do this. If you understand the idea that a positive delta H and a positive delta S both favor spontaneity, therefore it's spontaneous all the time, or a positive delta S and a delta H and a negative delta S is non-spontaneous all the time. And then if you can do the tiebreakers down here, so if delta S does not favor spontaneity, that would be spontaneous at low temperature because you need to decrease the impact of that. And if delta S does favor spontaneity, then you want to increase the impact of that. You've got the logic. Okay, now guys, are we all settled there? Please, Nora. Mm-hmm. Yeah.
Is that saying just like the overall charge of the temperature?
Yeah, let's not go with charge. Let's go with sign. Yeah, exactly. Yeah. Yes, exactly. But at the end of the day, if it's better for you to ignore this is really what you hear. That's a mess. This is the logic that you really need to have a handle on. So you could disregard this and just say, This favors spontaneity, this favors spontaneity, always spontaneous. This doesn't, never spontaneous. This doesn't, this does, this doesn't. So we need to make that smaller. This doesn't, this does. We need to make that higher. If you got that, you're gold. Is that okay? You guys okay? Yeah.
Kind of unrelated, like obviously on our lesson topic.
Okay.
Can we like define free energy?
Yeah, sadly we did. It is the thermodynamic function that brings, that's really it.
So it doesn't really have like an actual real life manifestation. It's more of just combination.
Yeah, no, yes, yeah. So, but in a very real way, it's a very real thing because it's really, at the end of the day, the thing that determines spontaneity. But in order to think about it, you really need to let your brain think about heat. And if you've ever thought about heat, that gets complicated. Disorder at some level is even easier to picture because you can picture messed up, right? But really, when you think about Gibbs free energy, you need to be thinking about how much change in Gibbs free energy, how much heat is something releasing, and maybe that's kinetic energy in your head, and then also how much disorder is it causing to go up or down. And bringing those two together, that's then Gibbs free energy. It is. It is a blended concept. Yeah, go ahead, Nathan.
I was going to say, like, all of this stuff is really theoretical.
Oh, yeah.
I was talking to my family about this stuff a little bit ago. Somebody brought up entropy, and they were very confused with the fact that not only that like entropies could be measured.
Yeah, oh yeah. Yeah, quantified in joules. Yeah,
In joules per degree Kelvin.
yeah, mole degree count. Yeah, crazy, right? It's very strange. Go ahead.
If we were to say that Gibbs free energy is sort of, kind of, measure of spontaneity, would that just be completely erroneous?
No, not at all. I mean, it's, I don't know that it's, and this actually, Adam, it brings us to an important point, guys. Whether you're finding this interesting or not, you need to understand this, because that could get you in trouble. So Gibbs free energy is not a measure of spontaneity. It is a predictor of spontaneity, and that's as far as we get with it. But in a very real sense, it's a measure of how much energy, including both heat and disorder, a system is exchanging as a process happens. But guys, this is where you've got to be careful. There's no such thing as more spontaneous. Did you hear that? So guys, if you do a delta G calculation and that number is negative, let's do this slowly. If you do a delta G calculation and that number is negative, is the reaction spontaneous? Yes. Now, what if you change the temperature and delta G becomes more negative? Is that reaction more spontaneous? No. It's giving off more energy. But guys, it is not, the rate doesn't go up. There's no such thing as more spontaneous. So either it is or it isn't. Is that okay? Yeah. Yeah, kind of. I mean, so the sign tells you the spontaneity, the value, the magnitude of the number tells you how much energy is being released, but it's the sign that tells you spontaneity. Is that okay? Okay. Maybe. Because now we got to answer Nathaniel's question, and it's your answer. So, guys, Nathaniel and Adam both got into this idea of what about ammonium nitrate? If we change the temperature, would it no longer dissolve? And I said, gosh, what if we knew the temperature? We can figure it out. Now, guys, and here's the big idea. You'll notice that in this, it talks about low and high temperatures and low and high temperatures, but we haven't said lower or higher than what. And so, guys, this is what you're going to see on the test. Goes like this. Say that you have, and I'm just making this up, say that you have a process and the value for delta H is negative 120. That's big. Now we'll go with it. negative 120 kilojoules per mole.
Do you not do this reaction on something relatively?
I know, I should make that smaller. Someone's gonna die. Negative 45. And then say that the delta S is negative 1,000. So guys, a couple things to talk about. Does a negative delta H favor spontaneity? Does a negative delta S? It does not. But what's missing from our delta S value? Units. And guys, this is where you've got to be careful. Your delta S values will be in joules. So you have to convert. We'll talk. But now guys, the question will say this. At what temperature range is this process spontaneous? At what temperature range will this be spontaneous? So guys, if you're working with me, we've got this. So guys, let's answer the question in general first. Delta H favors spontaneity. Delta S does not. So guys, what has to happen to temperature for this thing to be spontaneous? Big or small? Talk to the person next to you. Big or small?
In order for it to be spontaneous?
Does temperature need to go up or down? All right, guys, let's talk. So this is the idea. Delta S does not favor spontaneity. So to get this reaction to be spontaneous, we need to decrease the value of this part of the function. And so guys, to decrease this, temperature needs to go down. So this will be spontaneous at lower temperatures. Is that okay? Now guys, watch this. Ready? Delta G is negative. We'll do it this way. So guys, if delta G is negative, the reaction is spontaneous. What if delta G is positive? It's spontaneous in the other direction. What if delta G is 0? It's at equilibrium. So guys, that is the way that we solve this. And James, you alluded to this earlier. Guys, we need to know the temperature range at which this is spontaneous. In order to do that, what we do is we set it equal to 0. At 0, this is moving in both directions at once. That's equilibrium. Now, our delta H value is negative 45 kilojoules. Then, guys, our T is our X. But now we've got to talk about what we're going to do with our joules. And guys, you can go either direction. If I may offer a suggestion, I do not like converting kilojoules to joules, because if you do, you get 45,000 joules, and that number is just funny for me to work with. So rather than multiply this by 1,000, I like to divide this by 1,000, and now that is 0.1 kilojoules negative. Oh, I'm sorry, 1, my bad, 1. Sorry. Thank you. So guys, this is then just negative 1 kilojoule. So now we get to solve this thing, but guys, you're going to trip up on the signs. Be careful. So we've got negative 45, negative 1. They're all in kilojoules. So what we now have is negative 45 kilojoules. Wait. Oh, there we go. Plus, where's my plus? Plus.
Because the negative is positive.
Is that okay? So now, guys, we need to solve. So we bring this over. So that would be 45. And then our kilojoules cancel. And 45 is equal to X. So that is the temperature at which it is at equilibrium. But guys, that is not the question. But that's not what the question is asking. What it's asking is, in what temperature range is this spontaneous? So we would say it is spontaneous at temperatures below 45 Kelvin. And that is not inclusive. At 45, it's at equilibrium. Yeah.
So let's say you had this was our oxidation rate.
Okay.
We said it would be at exactly 45 Kelvin.
Yeah.
Would it have to equilibrium?
Correct. Yeah. Which in my brain kind of looks like water and ice at 0 Celsius.
Right.
But instead of freezing and melting at the same time, it would be dissolving and yeah. And actually there's a name for that. We're going to talk about it later. It's called a saturated solution. So in a saturated solution, you've put in so much solute that it can't all dissolve, so it sits on the bottom, but it's always dissolving. But that's not a temperature thing, it's a concentration thing. Yeah.
That's the fact that it's still
No, because they would both have moles in them. Yeah, if you really wanted to track units through this, the question is, where does the Kelvin come from? And this is actually kilojoules per mole Kelvin. And this is actually kilojoules per mole. And then your moles would go and you'd have Kelvin, and that's where the units come from. But don't worry about it. Yeah.
I don't know. We talked about the delta G being at equilibrium.
Yes.
So we decided that because we just decided, how did we
Why did we set it equal to 0?
Yeah.
Is that what you're saying? Okay, so the logic is this. So imagine that we have reactants and products. Okay, so reactants and products. And if you have a delta G that's negative, it's going from reactant to product. Okay, if you have a delta G that's positive, it's going from product to reactant. And so relative to temperature, what we want to know is the temperature at which it's doing both at the same time. Because if we can find, and that's what we're doing, right? We're solving for temperature. So if we can find the temperature where it's going both simultaneously, that gives us that middle point. And so if delta G is negative, it goes this way. If delta G is positive, it goes that way. If delta G is 0, it's going both ways. So if we can identify the point where it's going both ways, which is what we solve for, then between that and the logic that we use to figure out it would be spontaneous at low temperatures, we would say, here's our middle point where it's doing both, and then it's temperatures below that at which it's spontaneous. And did you follow the logic on why it's below?
Yeah.
Okay. Are you guys okay? Because that turned into a lot of I thought we were going to be done with like 40 minutes left in class. Instead of that, we have 4. So guys, this one's been really tricky. They have totally messed up all the homework for this. So I'm not even going to show you the homework from today. Wait until after school today to find the homework assignment, because right now it's really mucky. I'm going to work on that during 4th period, and then after school today, check for the homework assignment. So guys, we're going to take a break. We're going to come back and we're going to jump into lab. And then you know what we're doing, right? So on Wednesday, we're going to rewrite our tests, and then I don't see you on Friday. And then guys, on Monday, we're going to take the next unit test. Okay. So guys, let's just settle in for a minute. We'll go when the bell rings, we'll take a break, and then we'll come back to lab.